Today's topic is numerical optimization, and this is an idea that comes up a lot in applied math contexts because we often have functions that we want to optimize and perhaps constraints that we want to impose on potential solutions, and we want to find values that maximize or minimize the given function subject to the constraints. For example, we might want to maximize profits or availability in a rideshare program or whatever the case may be. Also, specifically in the context of machine learning, we often use loss functions to describe how poorly a model fits a given set of data, and then we want to use optimization techniques to try to reduce that badness in order to come up with the best model for fitting the data. So the fundamental idea that underlies most of these algorithms is gradient descent. So the concept is that we start at some arbitrary location and we move in the direction where the function decreases most rapidly. If we do that repeatedly, the hope is that we'll end up in a place where the function increases in all directions. In other words, we'll end up at a local minimum. And that might or might not be a global minimum, but gradient descent doesn't really solve that problem. It just tells us how to go downhill as quickly as possible. So the basic formula is that we start with some learning rate epsilon and some initial starting point x0, and we evaluate the gradient at our starting location, multiply that by negative epsilon, so we're moving in the direction where the function decreases most rapidly, and epsilon governs how aggressively we're taking those steps. So a large epsilon would mean we're taking big steps, smaller epsilon would mean we're taking smaller steps. There's going to be a trade-off there where if you take steps that are too big, you might sort of careen out of control and end up in some bad place, but if you take steps that are too small, it's going to take too many steps to get to the minimum. So there's perhaps some experimentation to do with the learning rate. In any case, we start at some location and then we take a step in the direction of the negative gradient and we make that our new position, and then we just repeat. So we increment the value of I and continue. So let's see this in action in the context of a specific example. So we're looking at this polynomial function that has roots at 3, 1, -2, and -3. And if we plot it over the interval from -4 to 4, we see it looks like this. So there's going to be two local minima, and one of them is the global minimum because the function increases to infinity in both directions as x goes to -infinity and to infinity. So if we want to implement gradient descent, the first thing we need to be able to do is take derivatives, and we can do that in a variety of ways. In this case, the function is simple enough we could just differentiate it by hand, but let's use the forward diff package from Julia, which implements automatic differentiation for us. So from the forward diff package, we'll import gradient. And the thing is, gradient expects to take a function that takes a vector as input, not a number. So if we want to use gradient for a single variable function, we have to do a little bit of setup. So we'll define our own function derivative that takes a function f and a value x at which to evaluate the derivative. And it's going to use the gradient function, but again, because gradient expects to take a function that takes vectors as input, we need to pull off the first entry of the vector x. So x we're going to have here as just a vector with a single element in it. So in order to plug that into the function f, we need to pull that element out. So that's what this anonymous function is doing. And then the value that we need to start at should be the vector that contains x rather than just x itself, because again, that's how the function gradient is meant to work. And then it's going to output a vector as well. So we want to pull the first entry off of that. So just to see this in action, if we take the derivative of, let's say, x squared plus 2x at 13, then we get 28, which is the correct derivative. So this is doing something that makes sense. And we can use it to implement gradient descent. So we're going to call our function grad descent, and it takes a function as well as a starting point. So that's going to be just some real number value, plus a learning rate epsilon, plus a threshold which establishes when we're going to stop. So we're going to stop here when the derivative gets small enough. We'll decide we're at a local minimum when the derivative is very, very close to 0. So our iterates are going to start out where we instructed them to start out at x0. And then we're going to run a while loop because we don't know how long this is going to take. So while the value of the derivative, so we need to define the derivative here. Let's just call it df, and we can just say that that's derivative of f evaluated at x. So while the derivative in absolute value is bigger than the given threshold, we're going to take a step. So we start with x, and then we move negative epsilon times the derivative at x. And that's our new x. And we're just going to repeat that until, again, the derivative is less than or equal to that threshold. And then we're just going to return whatever value we ended up with. So let's test this function out with this particular function f. So you can do grad descent of f starting at 0, the learning rate, let's say, of 0.01, and a threshold of, let's say, 10 to the minus 12. So we end up at 2.20, which is this value here. So it makes sense if we start at 0, we're slightly to the right of this hump, so we start to go down rather than up, and we end up here. And if we start somewhere on the left, like let's say -1 looks like it should work, then hopefully we'll end up at this value, which is -2 point something. And that checked out. If we want to see a full graph of this, we can do grad descent at each point x and just plot it. So what we'll do is plot from, let's say, -4 to 4 in steps of 0.1. And then to each of those x values, this function will get applied before the plot is made. So this is a trick for not having to repeat the x values. You make the x values your first argument, and then the second argument, if it's a function, plot knows that it's supposed to apply that function to each of those x values. And let's turn the legend off. And this makes a lot of sense. There's a value slightly to the left of 0, where if you're to the left of it, you end up at the 0 that's -2 point something. And then once you get past that, you end up in the 1 to the right. It's maybe worth pointing out what happens if you use the learning rate, which is too big here. Uh-oh, we got nothing. So let's just take a look at that sequence itself. Just look from -4 to 4. And what we find is that we get a bunch of nans. So things went sideways somehow. And what's going on here is that if your learning rate is too big and you're in a region where the slope is really negative, then you're going to be told to go very far to the left because you're multiplying that learning rate by the slope there. So if the learning rate is not small enough to keep that from getting huge, then you go way over here to the left. That has a big slope that's pointing down, so that's going to cast you way back to the right, and you kind of just like careen out of control here. So you do need your learning rate to be small enough for things to be well behaved. Let's take a look for a function of 2 variables. So this is called Himmelblaus function, and the contours look like this. So based on the picture, it looks like there are going to be 4 points here where there's a local minimum, and then the function just kind of increases as there. You can see it gets up to 2,000 up here in the corners, and it's down around 0 near these local minima. So we can use Senpai to solve for these minima exactly. And the equations we want to solve are just that the derivative of the function f with respect to x and with respect to y is going to be 0. So we'll just type that in here. Oops. So actually the method that is used returns complex numbers. It's using a formula for a radical formula for solving equations. And if you don't convert them to numbers, then you get these big complex expressions that have imaginary units in them. But if you convert them to floating point, then you'll see that actually the imaginary parts work out to 0 once it's all resolved. So you get 0 imaginary part here, here, for all the numbers. So we're taking the real part just to chop that 0 times the imaginary unit off. Anyway, we get these 4 points, and that checks out with respect to what's in the picture here, because it looks like those 4 points are going to correspond to these features in the contour plot. So to implement gradient descent for a function of 2 variables, it's going to be very similar. So we take a function f, a starting point x0, a learning rate epsilon, and a threshold. And we make the derivative just be the gradient of f. And then it's going to be a similar idea. So the derivative is going to be a vector rather than a number here. So instead of taking the absolute value, we take the norm. So while the norm is bigger than the threshold. And then same idea, x equals x minus epsilon times df. So we can check it out. So we can take grad descent. And this function f is expecting to take a vector as input. And the function we defined up here was more in the mathematical form where f takes 2 different arguments. So what we need to do is make a new function that wraps that old function but handles vectors. So the function starts with a vector v, and then it applies f to the first entry and to the second entry of v. And then we start at some point, like let's choose a point looking at the graph here, let's say 2, negative 2.5, so we expect to end up at this local minimum. And epsilon, let's try what we had last time, and threshold, same idea. And sure enough, we end at 3.5, negative 1.84. That's going to be this point here. So actually what we can do is plot a picture of where we end up for a bunch of different starting points and make a heat map of it to kind of get a sense of what's going on. And we're pulling out the first entry of the output here to get a real number which distinguishes the points. So we're saying we're going to distinguish these 4 points by their x-coordinate, because you can tell the 4 x-coordinates are different here. You could just as well use y or some other function that distinguishes these points. And what we find is that each point has sort of a square-ish patch around it, where all the starting points in that patch end up at that point. But there are also some points beyond that where the initial step is going to overshoot that patch and land us into this yellow patch. And similarly in all directions. So we see some green along this edge where we end up here, some dark blue here where we end up in this one, and similarly for this purple patch. So the next section is on constrained optimization. These are situations where we have to satisfy some requirements for our parameters, so we're not able to just choose them freely. And this is really the modal case for business applications. There are often reasons why you can't just use any old values of the parameters you want. And even in absence of some practical considerations that require some constraints, it's often useful to use constraints to specify how you want a model to behave, in addition to being able to specify an objective function. And the way these things work in practice is that very sophisticated solvers have been built, usually in something like C++ or Fortran. Some of them are commercial, there are some that are open source, and the packages that you'll use in something like Julia or Python or R are going to call this same set of solvers on the back end to perform the heavy lifting. And there's a very popular system called JUMP for encoding the problem and passing it off to the solver on the back end. And we'll see how to use that in the context of a simple example here. So consider the ellipse x squared plus 2y squared equals 1, and we want to find the point on that ellipse which is as close as possible to the point 1, 1. So let's just plot it and eyeball it. So there's the point, and this is the ellipse, and the closest point looks like maybe it's right around here. So maybe an x-coordinate of 0.6 or so, and then a y-coordinate of 0.55, something like that. So let's use JUMP to solve this problem. So we're going to use JUMP, and the back-end solver is going to be something called IP-opt. And the way you set up a model in JUMP is you use this model initializer. So it's a function that defines a new model. And it takes as an argument this object. So the object returned by the with optimizer function. And you specify which optimizer you want as well as any additional options. And we're setting print level to 0 here because the IP-opt optimizer gives us a lot of information by default. And we're just going to want the answer. So we store that resulting object as model, and then we proceed to make a bunch of macro calls. So at variable is a macro, and it just associates a particular variable, in this case x, with a model. So we make two new variables, x and y. Those are the variables in our problem. And then we just add a constraint. And the nice thing about JUMP is that you can just type the constraint the same way it looks mathematically. So x squared plus 2y squared equals 1. And then the objective function, similarly, you just type it in. So in this case, the objective function is specified as distance between the point and the ellipse, and we can just as well use squared distance, and that's what we're going to do. So x minus 1 squared plus y minus 1 squared is the function we're trying to minimize. And so we specify here as well that we want to minimize it. So this can be min or max. Then after we've got the model all set up, we call this optimize function on it. And it's got this bang here as a part of the name because it's indicating that the way that it's solving the model is by changing the internal state of that object so that the x and y variables are going to have values associated with them that can be extracted using the jump.value function. So this last dot here just means we're taking this function and we're mapping it over this array. So that's just applying the function to each element in the array. And so we're going to extract the x value and the y value. And we find that the point is about 0.68, 0.51. So our estimate was a little bit off, but pretty close. The last topic is convex optimization. So the idea here is that there are a lot of things that can happen when you optimize arbitrary functions over arbitrary domains that make it very difficult to find a global minimum. However, if the problem happens to be convex, meaning that the function is convex and the domain is also convex, then a lot of great things happen. If you find a local minimum, then that's actually also a global minimum. And furthermore, if the function is what's called strictly convex, which we'll talk about in a minute, then there's only going to be one local minimum. So you just apply any gradient descent algorithm. It's going to take you to a local minimum. That's going to be the global minimum, and your problem is solved. And actually, behind the scenes, some of these convex solvers are using some more sophisticated algorithms that leverage some specific properties of convexity. But you don't have to worry about that too much. The main point is that if you have a convex problem, solving it is going to be much more robust. A set is convex if it contains all the line segments containing 2 points in the set. So you take 2 points in the set, you draw the line segment, connecting them, that whole line segment needs to still be in the set. So things like circles, regular polygons, triangles, ellipses, there are a lot of possibilities. And we say that a function is convex if the region above its graph is convex. So whenever you connect 2 points on the graph, that whole line segment needs to be above the graph. If it's all above the graph except the endpoints, then the function is strictly convex. If it maybe touches the graph in more places than 2, then we would just say it's convex. So we have this general form for a constrained optimization problem. We want to minimize a function f, and we're applying some constraints, including some inequality constraints, which we're going to write as gi of x is less than or equal to 0. And the idea here is that any inequality constraint can be written in this form, because what you can do is just move everything from the right-hand side, if it's a less than or equal to the left, and fold that into your function g. And if you have a greater than or equal to sign, you just flip it and then do the same thing. You might also have some equality constraints, and we'll write those as hj of x equals 0. And the same idea, whatever your equation is opposing an equality constraint, you can move everything to one side and call that side h. And the point is that if f is a convex function and these are both convex sets, then it's a convex optimization problem. And the considerations above apply. There's going to be at most one local minimum if it's a strictly convex, and in any case, every local minimum is also a global minimum. So let's maybe get a little bit of graphical intuition for that, why that's true. So this function e to the x squared plus y squared over 10 is convex, and we can plot it and see what's going on and why it would make sense that there would be a minimum. So if we plot it over the box from 2 to 4 squared, so the x runs from 2 to 4 and the y runs from 2 to 4, then we see it sort of like sloping down, and it has a minimum down in this corner. So that's one possibility. And if we plot it over a different box from -2 to 2, we see some other possible behavior. If this was a domain of interest, then the minimum would be interior. It would be right in the middle of this box, actually. But in either case, you can't have a situation where you have distinct local minima, because if you connected those local minima, then the graph of the function would have to be below that line, and the higher up one would not be a local minimum. So we're also asked to look at this other function, minus e to the minus x squared minus y squared. What we see is that the graph has this sort of upside down hat shape. And if you connect a point like this one with a point like this one, then the graph of the function is not lying below that line segment. So this function is not convex. And we could certainly choose particular numbers x and y and plug them in and see that that's going to be the case. But from the picture, it's really clear. You're going to be able to connect points on this graph with a line segment and have that line segment cut below the graph in some places. Notice that this function nevertheless does have a global minimum. So nice convergence properties are not unique to convex functions. This is also going to be a function that's very easy to minimize with a gradient descent algorithm. In problem 5, we're looking at this fairly generic optimization problem where we're trying to minimize this particular linear combination of the entries of C, the vector C. And the constraints are that x has to be, after applying a1, it has to be inside the sphere of radius square root of b1. And it has to satisfy this linear equation. So again, it's quite a generic situation. We have a constraint on the norm of some linear transformation applied to x, as well as a system of linear equations imposing a constraint on x. And we're trying to minimize some linear combination of the entries of x. We just want to see what this looks like in JUMP. So most of the setup is done for us. We're given a random matrix. This equality vector on the right-hand side of the equality constraint is also random. And we're just supposed to put the objective function in and the constraint equation. And the objective function is just going to be C transpose times x. That's what's specified above. And the equation is going to be a2 x equals b2. And we use this point equals because we're comparing vectors here. So a2 times x is a vector, b2 is a vector. And in Julia, when you want to compare two vectors and make sure that they're equal in every component, you have to put the dot in front. So we don't need that for the other constraint equation because this resolves to a number. So this is a vector transpose times itself. That's going to be a number. We're making sure that's less than or equal to b1. And otherwise, we're just running the model here. So notice we're setting the random number generator seed so that everybody gets the same results. But it's the same basic flow. We create a model. We set up our model by defining variables, adding objective functions and constraints. Then we optimize the model. And then we're just going to extract the values of the vectors. So we get our solution, and we can read off the value of a2x and the norm of a1x. Notice that it's not quite perfect here. It did bleed over a little bit past 1. This was supposed to be less than or equal to 1. So it's just approximate. So the last part says, think of a business situation where you might want to maximize an expression like C transpose times x. So in my mind, the canonical example for this sort of thing is that the C vector is containing something like prices of a particular good. So maybe you have 10 goods that you sell and each one has a price. You put those in this vector C, and then when you multiply that by x, the entries of x are corresponding to perhaps how many of each of those items you sell, in which case this total product would be revenue. It's multiplying how many you sell times the price of that item and then summing over all items. You might have a constraint on x of the form ax equals b if you have some linear combinations of x that have to be equal to some particular value. Like you might have a contract that says that you're supposed to sell exactly so many of a particular set of items. So maybe items 4 through 7, altogether you have to sell 100 of those. So that's a linear equation. You might have several of those. You can package those linear equations together into a single matrix equation like this one, and then you can pass all of that into JUMP to solve for you, just like we did here.